In this video, we're going to show the following fact. If W is the subspace of Rn, then Rn is W plus W perpendicular. Let us prove this. So, let's see. W is the subspace of Rn, so how about we say let the dimension of W equal M. Okay, well then clearly our W has a basis consisting of our M elements. And W has their basis with M vectors. By the Gram-Schmidt process, we can transform these vectors, these M vectors, into an orthonormal basis. Okay. How about we say let S equal W1, W2, all the way down to Wm be this orthonormal basis. Or for W, of course. Okay, because the original basis was for W, we used the Gram-Schmidt process on this basis for W, and now we have an orthonormal basis for W. So now here's what we need to do. If V is a vector in Rn, we're going to let W equal to V dot W1 times W1 plus V dot W2 times W2 all the way down to V dot Wm times Wm. And we're going to let U equal to V minus W. Now, where are we? So, since W is a linear combination of the set of vectors in, I'm just trying to find the set in S, so set of vectors in S, then little w must be in W. These vectors are a basis for W, and if I write little w as a linear combination of the basis vectors, then W is in W, little w. Okay, little w is in W since little w is a linear combination of the vectors in a basis for W. So little w is in W. Okay. Now, what we want to show is that this vector U is orthogonal to every vector in W. Okay. We will show that U is orthogonal to every vector in in the set S, or basis, excuse me. Okay, so let us do this. So we're just going to look at one WI for WI. Now, if I show that, where are we? If I show you that U is orthogonal to an arbitrary vector in S, then it's orthogonal to every vector in S. Okay, so how about we say it this way in that case? For each WI in S, we have the following. We have that U dot WI is equal to the following. U is V minus W dot WI. Distributing, this is V dot WI minus W dot WI. Okay, well this is still V dot WI. It's this piece minus W dot WI. But W dot WI, well, right here is W. So it's minus W, which is V dot W1 times, or W1 plus V dot W2 times W2, all the way down to V dot WM times WM. Well, that's just W, and I dot this with WI. But remember, the vectors in this set are orthogonal. So what we get is V dot WI minus this dot W1. V dot W1 times W1 dot WI, all the way down to V dot WI times WI dotted with WI, all the way down to this vector V dot WM times WM dot WI. Now most of these are 0 because we're in an orthogonal basis. This is V1, W1. Well, this is 0, and this is 0. The only one that's not 0 is W1 dotted, or WI dotted with WI. So we get V dot WI minus what's in the big brackets, which is nothing more than V dot WI times WI dot WI, V dot WI. Now here's the key thing. For all I, that's 1. The WI came from an orthonormal basis. So this is just minus V dot WI. And look at this. We do get 0. Okay, so U is orthogonal to each and every vector in set S. It's orthogonal to every W sub I. Okay, so now what does this tell us? Hence, U is oops, that's not orthogonal. U is orthogonal to each and every vector in S. Okay. And therefore, lies in W perpendicular. That makes sense. Okay, now somewhere we said that U is equal to V minus W, which implies V is equal to U plus W. Okay, now this was V was just an arbitrary vector in R. And this is in, give me a moment, this is in W perpendicular, and little w is in W. Hence, V is in, I'll just write it in this order, W plus double perpendicular. Now, by the previous theorem, we know that W intersect W perpendicular is just the set that contains 0. And that's all we need. So, okay, so we have an arbitrary V in here. So let me put that here. Well, we have an arbitrary V. That means that Rn is a subset of W plus W perpendicular. But this can't be bigger than Rn. This cannot be bigger than Rn. So it's equal to. Okay. Now that we have that, this statement here, along with this statement, so Rn is equal to W circle plus W perpendicular. And that completes this proof. Again, to go from plus to circle plus, all I had to do was know that, or show that, the intersection of those two sets is just the set that contains 0. But that was our proof from earlier. This completes the proof. If you like theorems like this and seeing their proof, please subscribe to my channel. Like my channel as well. If you like to leave a comment about something I did right or wrong in the video, something you liked, disliked in the video, if there's a video you like for me to make up, leave the comment. See you guys in the next video. Watch and learn.